All right, everybody, happy Friday. Home stretch. A few more hours to go. I'm already getting the coffee. Anyways, today we have Pete Marchetto presenting. Pete has been on basic biological and environmental research, specifically swimming and up along the Mississippi. He right now collects data from the natural environment and tries to utilize that data and data processing in order to make certain decisions. Of particular interest to him are open source biological problems, specifically within the fields of agriculture, silviculture, and natural resource management, where sensing systems will allow for new data to answer older questions, such as steam gauging, water and air quality assessment, and in regions drastically affected by climate change. So, if you can please give a warm welcome to Pete.
Thanks very much. I'm going to actually step back and let you watch a brief intro video that might even be a better intro to my work than I am. But then again, it stars me, so who knows. However, I just realized that apparently our sound is not working here. Well.
Wait, the sound doesn't work?
Yep.
Did you want me to fix it?
I'll just point the mic at the speakers. Do this. Anybody name that theme song? It's kind of a default video for me because of the fact that it runs through a whole bunch of different things. What I do is I build sensing systems, but I do it a little bit differently from a lot of other people. I build them specifically so that they can be immersed, sometimes literally, in an environment and take measurements of that environment. So what I want to do today is go through the needs that I normally address, the theory behind the sensing systems that I build, the building of those systems, bridging, which I'll get to what that means when we get to that section, setbacks, some of which are kind of funny, and the future of that research program that I run at the University of Minnesota and all of the collaborations we're hoping to have. So, the needs are mainly in ecology. Well, originally I had this list so that I also included agriculture and silviculture and fisheries, and then I realized that all of these are, in essence, applied ecology. Ecology occurs in two places from my perspective, in the built environment and in the natural environment. Then in the natural environment you have two further subsections. It's either the cultivated or the wild portion of that natural environment. Here's an example of a built environment system that I've done. This was inside of a high tunnel. Any of you here ever work with any sort of horticultural work or ever do anything with plants? I see a couple of hands. Anybody been inside of a greenhouse? A few more hands. Anybody know what a high tunnel is? Okay. So a high tunnel is, in essence, a greenhouse made out of plastic. It's just a piece of 6mm sheeting stretched over a very large frame, as you can see in this slide. And this frame, in this case, is about 20 feet long, 20 feet wide, 30 feet long, and about, I think we were at 17 feet at the top of the center. Now, the way that this operates is that you're able to roll up the sides, and we also have fans over the doors on both ends. What we needed was a way to continuously control the temperature inside of this high tunnel. You see, at the time I was doing my PhD work at Cornell, and I was working with this guy who's actually from the Twin Cities, Josh Serra, in landscape architecture. And Josh had this brilliant idea. Let's show people what climate change is going to do to their gardens. Let's do that by simulating the temperature rise that you get in the year 2050. Come on in, guys. I think there's a couple of seats. Simulating the temperatures you'd have in 2050, and just having the same sorts of beds of plants, both inside and outside the greenhouse, or the high tunnel in this case. The thing was that we were counting on the temperatures to be exactly 5 degrees higher. And if we hadn't have gotten that 5 degrees, if we had overshot, which would normally happen with this tunnel, then we would have screwed up the experiment royally and nothing would have worked. Furthermore, originally in the first year this ran, before I was involved, we were having a student apparently run down there, I think it was 2 times a day, hook up these 40 amp 12 volt winches on the sides of the thing to a car battery and raise the 6 mil plastic rolls with about, I want to say it was somewhere on the order of about 500, 600 foot-pounds of torque, all the way up to the top. And it was a very binary system. It was either all the way up or all the way down. So what I had to do was figure out a way with the rest of the team there that we could actually control this thing. So that mess of wires that you see in the inset there was our solution. Are many of you from the Twin Cities area? A few, okay. How many of you know of a store by the name of Axeman Surplus?
Yeah.
Oh yeah, okay, good. That's where I got the large clackety-clack industrial relays that handled those 40 amp winches. Because that's about the only thing that you can do. Other thing is that we actually were able to make it bidirectional. If any of you are really into lower level electronic design for power, you'll be familiar with H-bridges. We basically implemented one of those in relays, and it was glorious. It sounded like being in an old phone exchange back in the day. But the best part was that we partnered inadvertently, because they didn't know they were partnering with us, with Particle. And we used their photon board and a Wi-Fi hotspot from, I think it was, we tried at AT&T, that didn't work because of the area, and then Verizon, and we were able to get complete access. We were able to program the entire thing over the air, and we were able to control whatever temperature we wanted, even to the point where we could actually create heat waves, where we could say, all right, well, ignore the temperature sensors for this particular amount of time, or unless you're above such and such a temperature. Anyway, long story short, it was a very nice system, still running up there at Cornell, and still informing people of just how screwed their gardens will be in certain ways and how incredibly productive they will be in others. For example, Minnesota right now is, I believe, the fastest warming state. We are at, I believe it's 11.2 degrees per century at this point. So your pepper plants will benefit from global warming. I can tell you that authoritatively. Now, this is from a place that I actually went to back when I was in first and second grade, the Homestead School in Glens Bay, New York. And I came back there to teach an electronics and IoT seminar to their 5th through 8th graders. Now, normally, a lot of you might think 5th through 8th graders, and that seems a little young. These kids were amazing. They built this entire stream gauging station that I designed, and we managed to build the entire thing, once again, thanks to a particle photon, for on the order of about $400. And consider that the USGS has stream gauges out throughout the entire country. But the thing is, they're not really stream gauges, they're actually river gauges. They're on larger bodies of water. And they can measure down to, I believe it's 1,000th of a survey foot, what the height of the water is. The surface roughness of most streams when they're flowing is closer to 1/100th of a survey foot. The resolution we were getting was less than that of the surface roughness of the streams we were working with as well, and we paid $30 for our depth sensor. A little tiny infrared distance sensor from Sharp inside of a PVC pipe with a ping pong ball, which sounds insane. That shouldn't work that well, except for the fact that ping pong balls are actually manufactured to a very precise tolerance. 38 millimeters, I believe, is its radius or the diameter. Anyway, the diameter is controlled to within 200 microns. The weight is controlled to within milligrams. You'll see this as an ongoing theme in my talk. Whatever you do when you are prototyping, push the precision of the manufacturer of parts up to the next level above you, your supplier. If you can do that, your prototype will be cheaper and better than the next guy's. So what we wound up doing here was basically taking a very precise float, putting it under a $15 distance sensor that Sharp actually rates for 1 millimeter accuracy, and finding that we could actually get plus or minus 2 millimeters on stream depth, which, when built by 6th, 7th, and 8th graders, is a pretty miraculous thing. The rest of this, we built our own conductivity sensor out of 2 pencil leads. Why pencil leads? Well, because of the fact that pencil leads too have to be precise down to a couple of tens of microns in order to fit just right into a mechanical pencil. And they have to be exactly the same hardness, which means the same amount of graphite, which means the same conductivity. So you see where this is going. Now, there is also another picture on here. In the natural and cultivated world, you also have to deal with livestock sometimes. Another project I've worked on that was IoT connected was the one where a sheep was texting me at 3 a.m. My wife got really annoyed and yet amused at the sheep. I was at the Cornell Lab of Ornithology in their bioacoustics research program, and we wanted to find out what exactly was happening to the sheep on Cornell's teaching and research farm. You see, I keep saying Cornell. I was there for about 7 years, and despite being an Ivy League, they're also New York's land-grant university. So all this crazy stuff in the outdoors, they love it. They're also the only Ivy that loves it, so they're the only Ivy that I'd go to. Anyway, this sheep has a satellite-connected backpack on, and it's measuring 4 parameters. Sound pressure level, which is the main thing we were after, temperature, barometric pressure, and relative humidity. And then the tag went offline. I come around the following morning in a bit of a panic, wondering if the sheep has lost it somewhere in the pasture, or if it got dropped in the road or whatever. No, the sheep is laying down on top of it. She was tired. She fell asleep on top of the tag after somehow pushing it over to her one side. So after getting some help to finally corner said sheep, if you're ever trying to get one sheep out of a flock, have at least one other person, because of the fact that it will take some doing. You have to get them cornered against an obstacle, and then there have to be 2 of you, otherwise the other sheep in the flock will try to swarm between you and the sheep you're after. I could get into the whole game theory behind it, but I don't really want to. Anyway, needless to say, this ewe was very helpful eventually. And we did find out that the sheep do indeed move away from the road next to the farm during rush hour, and they generally try to move away from loud noises. So, I hate the phrase intuitively obvious, but it kind of describes my work in that case. All right, natural wild ecology. This, to those of you from the upper Midwest, it may look familiar. Anybody in here go ice fishing ever? A couple of people, okay. My students named this device on the bottom left Rooster. It was deployed on the Chinese New Year this year, so Year of the Rooster, hence the name. And Rooster is a strange object. It is a polyethylene terephthalate foam island that is designed originally to just float in a lake become an anchor for biofilms that then take nitrogen or nitrates from fertilizers out of the lake and basically bioremediate the lake so you don't get these harmful algal blooms that you often see. If any of you have ever heard of the Lake Erie algae blooms, which have actually sickened many people, especially around Toledo, that's the sort of thing that happens. You have too much agricultural runoff into a stream that goes into a lake. This algae starts eating the nitrates and the phosphates that come off of that. These islands are designed to combat that. And what we wanted to do was find out whether or not these islands would last through a winter. We got done building ours too late, so some of my students went with one of our other faculty members up to Fleming Lake in Aitkin County, out in the deepest north-central Minnesota. And, well, my colleague Joe Magner cut a hole in the ice and tried to keep cutting that hole in the ice with an 18-inch bar chainsaw. The ice was over 2 feet thick. I said, Joe, when he was about to head up there, you certainly got the right chainsaw for this? Oh yeah, it can't possibly be more than 16 inches thick. You certain? Oh yeah, I'm fine. Well, Pete, we had to borrow an ice auger. Did you now? Oh, your student Kieran had to get after it with the pickaxe. Did he now? Yeah, that was a colorful and fun adventure. So this was basically a piece of foam that had a bunch of force-sensing resistors around the side of it. You can buy these force-sensing resistors for about, I think it's $8 from DigiKey. And what we found is that they're rated technically for 0 to 4.5 pounds. And in reality, they go from 0.5 pounds for the beginning of the response to well over 200. Especially if you do what we did, which is sandwich 2 of them together. So what we were able to do was basically track how much force the ice was putting on the island from each side. At the same time, also monitoring the temperature above the island, in the island, and below the waterline. But there's one big problem. You see, this is northern Minnesota. This is wintertime. Our lows, even without the wind chill, can sometimes be below negative 30 C. Crossover temperature is negative 40. Fahrenheit is the same as Celsius. So let's think about this for a moment. How do you stop a lithium battery from freezing in the middle of a Minnesota winter's night when the wind is howling? Any ideas?
Put it in your pocket.
But what if you're not there? What if you got an unmanned, autonomous IoT station reporting back to you?
Hand warmer.
And what if you have to have it doing this for 6 weeks at a time?
Drop it in the water.
Yes, it's actually exactly what we did. My student Emily came up with this brilliant idea, which is, this is a freshwater lake. The water that's not frozen is still at or above 0 degrees C. That's well within the operating range of our battery. Let's just epoxy it into a box, drop it in the water with a weight on it, and then run the wires up to the surface, and it worked perfectly. I mean, there was a little bit too much pressure, so after a longer amount of time, some wire actually started to seep in the seal. So don't trust those IP67, 68 boxes you can get off of Amazon. They're actually more like IP65, 66. Anyway, it was a great experiment, and Emily, despite being a junior undergraduate, came up with an idea that her advisor, me, and the graduate students and postdocs and everybody there couldn't have come up with. That's the great thing about having people with different perspectives working on a project, and that was one of my biggest lessons from this. Everybody will make a contribution. Now, we're going to skip over to a little bit of theory here. I am a pedant when it comes to names of things. My apologies. So how many of you here think that a sensor means a thing that you put out that sends back data from something being sensed? Okay, I'm going to blow your minds. Okay, maybe not. I'm just going to be really pedantic. A sensor is a transducer. A sensor is the part that changes something from the outside world into, for most of us, an electrical or optical or mechanical signal. It is a means of converting one form of energy into another. The sensor then gives us the sensed signal, S of t, a time series or time domain signal. That then goes to our analog to digital converter, or if we're just modifying a switch, that goes to our input-output, or input usually. That then encodes the data that we have into a number, which is either a 0 or a 1, or some combination thereof into a larger number, d of n. This is our data function. And then that goes in, usually, in my case, to a microcontroller, which then performs some operation on this data to either put it into storage or to put it into a transceiver. That transceiver then encodes the encoded data in some way and then sends it to another transceiver, which eventually sends it to the cloud. So mathematically, you're taking a function, you're operating on it to change it into another domain, mainly in this case you're discretizing it, and then from there you're operating on the discretized function. Step back from this for a moment. Which part of this is the sensor? It's only the part that gives you the SFT function. The rest is the sensing system. When you take the whole thing together, that's the instrument. These are the three terms that, more than anything else, I want you guys to get out of this talk. So, a little bit more theory here. A transducer usually has a whole network of electrical components that are implicitly built into the wires and the network around it before it even gets to your analog to digital converter. There's always impedance of some sort that's mixed. So what I'm getting at here is that there's a whole bunch of stuff that happens to signals coming from sensors. The reference voltage in your analog to digital converter, that changes with temperature. The frequency that you're sampling at, that is actually proportional to the square of the temperature and has a negatively curved quadratic relationship. Don't get me started, I wrote a patent with people at Cornell on this one, and it was one of the most insane topics I've ever worked on. Don't send me back there. Your inductance is going to change as things expand and contract with temperature. And in Minnesota, we experience temperature. Capacitance, resistance, so resist, much screw up, such temperature, very uncertainty, wow. So, back to our theory. That means that a value that we're trying to measure is equal to a least significant bit count, essentially our binary number, times the voltage that we're checking that against over 2 to the n, where n is the bit depth of your encoding, times some inverse calibration function, something that gives you volts versus, say, meters or pH or something like that, because we're usually measuring in voltage. Unless you're one of those weirdos who happens to measure in current. 4 to 20 milliamp people, I'm looking at you. Sorry. Except that's wrong too. Uncertainty! So, variance occurs within any system. You always have some amount of noise that occurs within your system. So there's always going to be some uncertainty in your numbers. And I want this to be another thing that you get out of the talk today. You have never made a measurement, especially in the environment, unless you have done two things. Number one, you have converted back to the original units that are useful to people, like meters, or NTUs, nephelometric turbidity units, for how turbid water is, or relative humidity, temperature, any of these things. Number two, your measurement is not complete. Also, unless you have an uncertainty, a plus or minus after that number. If you don't have that, your number means nothing to me because I don't know what to compare it to. I don't know how uncertain I am about the measurement that has been made. How uncertain we are traces back to the measurements that we use. The basic measurements come from the Bureau International Poids et Mètres. I believe I'm pronouncing that very badly. In France, just outside Versailles, where they have international standards. Then you have next generation standards laboratories like the National Physical Laboratory in the UK, or NIST, the National Institute of Standards and Technology here in the US, or NRC, CNRC in Canada. And then that goes to primary manufacturers and their primary calibration labs. And what happens is generation after generation you establish a chain of traceability, very low uncertainty measurements created by standards against which things that you build can be compared to know that a volt truly is a volt, plus or minus some number of very, very small microvolts. And finally, in the theory, I wanted you guys to understand that this is another thing we always have to do, at least in environmental sensing. Relative measurements are not for the faint of heart. Absolute ones are even worse. You always have to have a standard and a device under test, measure the two of them, see what the deviation is. Up there on top, I have two different Gaussian distributions, very, very roughly Gaussian. Both of them have the exact same average value, but the uncertainty, the sigma value, is very, very different. The population of possible measurements that are under each of those curves can have a much larger or much smaller distribution. So, building stuff. Step 1, prototype a cheap sensor. Step 2, connect to IoT dev board. Step 3, characterize at least 4 values across that range I was just showing you. Step 4, confusing myself with a 4. Create calibration function from the regression. Step 5, try calibration curve from more values. Step 6, deploy. Step 7, profit? Bridging. Now this is something that I've been doing with my research program since I was at Cornell. Getting other people involved in building for me because of the fact that I don't want to build 20 million sensing systems on my own. So I design and build them cheaply the first time. I document a design for manufacture. Then I get people from the maker crowd and people from the environmental crowd together in a room, and I have them build together. The electronics and maker folks get to learn about the environment. The environmental folks get to learn about electronics. Everybody comes out knowing something they didn't know before they went in. It's like a cage match for brains, I guess. Only the exact opposite. So then after that, we deploy and calibrate, calibrate and deploy, strike that, reverse it, our sensing stations. We reconvene the group, though, then to discuss and revise the design. And on an annual basis, you hold another workshop, you lather, you rinse, you repeat, you wipe hands on pants, and you say, every year I'm going to make this thing better. So, let me briefly go into my setbacks because I know I'm running short on time here. Number 1, don't trust cows. These cables were in a tree next to a stream in upstate New York. Cows came over because this was in the middle of a pasture and munched on them. Cows apparently like cables as floss. Don't trust cows. This was recorded when we were trying to record sounds from African forest elephants in Gabon. That's the ooking part, the vocalization. Oh, and here comes the rock. Number 2, don't trust chimps. Third thing you need to know as engineers, anywhere in the world, 2 words remain true above all others. Data sheets lie. This happened because of that. Number 3, don't trust ratings. Always multiply out by a few orders of magnitude if possible, or at least by a whole integer, how much you think you'll need to actually get what you'll buy. We had this solar charger, or charge controller for a battery and a solar panel, and it said, oh, I'd be fine with 600 watts worth of input power, even on a cloudy day. Yeah, that was 500 watts that made that thing warp like that. So in the future, my lab's going to endeavor to create more sensors and sensing systems to go into more sensing modes for outdoors. I'm going to be working on figuring out development board characteristics. Like, for example, right now we're doing temperature characterization of Arduinos to see how much the clock or how much the analog reference voltage changes with temperature. And believe me, it's a lot. Nice thing is, though, the thing that I said that I had a patent on before about the clocks, you can apply that to this too, where you can back out what the correction factor needs to be for a temperature once you've done the characterization and you measure what the temperature is while you've got your thing deployed. Over at the University of Minnesota, I'm already working on starting a calibration lab, so if any of you wish to collaborate and get your stuff calibrated so you know that your measurement is real, rather than just something that's coming off the manufacturer's data sheet, because let me hear those two words, data sheets. Thank you. Wow, that was a nice moment. Last but not least, if any of you are interested in doing anything outdoors with your things, anything with your never mind. I'd love to partner with you to create any sort of products that you guys would be interested in working on. With this, I'll give some brief acknowledgments. The whole team at the Instrumentation and Robotics Lab, which I co-direct with C. Yang over at the University of Minnesota St. Paul campus, the Cornell Soil and Water Lab, where I did my postdoc and my PhD, along with the Bioacoustics Research Program at Cornell. Dirk, Vic, and the gang at Wicked Device, who got me into the beginnings of trouble with IoT with their wildfire board. Even the guys at Particle, you should probably check that thing out. It is pretty cool. It's actually got 2 Atmegas on it for some reason. And that some reason is that one's being used as a watchdog timer and watchdog state monitor for the other one. Built-in Wi-Fi. Anyway, good stuff. The Ithaca Generator Makerspace, the Homestead School for hosting my workshops. MinDrive, especially Saad Bedros, if Saad is here. Saad's the one who got me invited to this event to talk. So, I know, much to your detriment, I'm sorry. Ralph Hutt, John Lehman, and the late Bob Warner for helping me with bouncing ideas around. And the UMN St. Anthony Falls Lab, which I'm an affiliate faculty member at, also helped me a great deal with figuring out just what sensors are needed for any endeavor with water. So with that, thank you very much for your time, and if there are any questions. Thanks. Yes?
I just have a question if you have information to share later with stream gauges and how you built that show cheaply. Yeah, I'm just interested in like Devil's Kettle mystery up in near Duluth.
Yes.
So apparently hydrologists were able to solve it, and so I was just wondering how repeatable that would be in terms of citizen science.
Well, the first thing that you have to consider is the fact that Garmin now has a $120 sonar unit that you can drop into virtually any body of water to help map.
Really? Okay.
And I'm still working on trying to figure out the serial protocol, because the $120 model doesn't actually give you data out, it just goes to the screen. But insofar as tracking goes, you may want to buy one of the asset tracker kits from my friends at Particle, hint, hint, plug, plug, because of the fact that those, I believe you guys ship those with an IP68 rated box, don't you?
Yeah, that sounds right.
Yeah, so you could put that in Devil's Kettle, and wherever it comes back up on the other side, as long as it's weighted properly, relatively just above neutrally buoyant, you could get it back out. But that being said, if you're actually interested in monitoring water quality rather than water trajectory, that's more the sort of thing that I've been into.
Yeah, I guess what I'm interested in is the way the hydrologist did it is apparently like the flow of the water rate, flow at the top versus after it comes out on the bottom.
Oh, Q high versus Q low.
Yeah, and
okay.
saying the tolerance was within a certain amount, but apparently they're the only ones that have done it, the DNR's hydrologists. So I thought it'd be interesting to
it would definitely be interesting.
5th, 8th graders to try to replicate that.
It would be a good idea, and actually I'm supposed to be running a stream gauging workshop up at UMD at some point within the next year or so.
Cool.
My contact info is on the website here, so just email me to remind me that I should look into that at some point, please.
Sounds good, thanks.
Any other questions? Okay. Well, thank you very much.